Hey, I've got a question for you in Vectorland. Is the world flat? Have all those sailors always come back, or did they drop off the edge of the Earth? I think they came back, and it is a 3D world we live in. And this will give you an idea. This set of axes, 3D coordinate system here, extending the plane 2D to 3D. So I think you can see what we're going to do here. We're going to extend all our ideas of vectors into 3D. What things change? Can you find the distance between points and therefore the length of a vector OP and things like that? That's what we're going to investigate. And looking around the screen, I think you got a clue as to how you might find the vector between 2 points, or displacing A to B. And let's have a look at that later on now. So let's go and investigate this 3D coordinate system here, which you haven't seen before. And come down here, and I'm going to do a little bit of plotting. Now, I had a choice. I could have put a static diagram up, as I did in that previous screen, or I thought, well, you might like to see me do some work, hey? So I'm going to plot the point 257. I think this is a good exercise for you understanding the coordinate system. Now, this is the X, this is the Y, and this is the Z coordinate, but look at the axes. Alright, there's the X, then the Y, like the Cartesian system being laid down, the 2D system being laid down on a flat plane, and the third coordinate is the Z above that plane. So this is what we need, for example, if we want the flight vector of a plane. If we just want the direction vector of a ship, 2D will do, won't it? The flight vector of a plane, we need 3 aspects or components to that vector. So let's have a look at the point 257. So I'm going to just draw a little scale in here. So there's 2, 3, 4, 5. And you might see what I'm doing. I'm going to just plot this point 4, 5, 6, 7. Okay, I'm going to plot the point 257. So let's do it. We've got to move 2 out here, down here in the X. So let's do that. And I'm going to make it a 3D picture here. 2 in the X and then 5 in the Y. So coming out here, I'm going to come then out to there. Then I'm going to elevate at 7. So I've got to go up here. Okay, so I'm going to box it so you can see the 3D nature now. Are you getting it? Okay. 2 out here, 5 along here, and then 7 up. So I've gone to there, and that's my final point up here. Point P 257. So if I was to draw the line OP, that would be giving me the direction vector OP, or the position vector of point P. Let's have a look at that now. So that position vector would come from O out to P. Okay, from the origin out to P. And that position vector would be written like this. Now, position vectors have the same 3 components, don't they? Because they're coming from the origin out to the point. That's my vector OP. So my position vector of point P, OP, is 257. Okay, so we can do the same things in 3D as what we were doing in 2D. So what about lengths now? Can we find the length of OP? What would that be? Okay, well, let's have a look down here. I'm going to draw some triangles down in the bottom here. So there's one. And then I'm going to draw one up here. So I'm going to work in this triangle for a start. What do you reckon by Pythagoras that length is? Just remember, these axes are at right angles. Isometric drawings like this don't show the angle accurately. By the way, just a little point, if you're doing any work, you don't draw the vectors in 3D land. Too hard. Okay, we don't usually draw them. We work with the algebra of them. So what is this by Pythagoras down here? Well, let's call it what can we call it? Let's call it m squared equals 2 squared plus 5 squared by Pythagoras. Okay, and then coming up into this triangle, okay, what is the length of that side? The size of OP squared equals, well, we want the square of this side here, m squared, so we want that. It's m squared plus, what's this? 7 squared, again by Pythagoras. So m squared is 2 squared plus 5 squared plus 7 squared, or the size of that vector OP is the square root of 2 squared plus 5 squared plus 7 squared, because OP is greater than 0. It's not plus or minus that root, solving that squared equation there. Okay, wow, that's easy. That's just the same as the length in 2D with an extra component squared and added. So Pythagoras has done it for us again. You just notice here that this is a 90 standing up there as well. Okay, so the length of OP, that's good, that's good. Nothing new there, just adding the third component. And we've actually tried to prove it there. Why don't we go and have a look at another one where I've got 2 points, not a position vector from the origin. Let's go and look at what it looks like between 2 points on the plane. So I'm going to do it all again. So let's have a look now at that. This time let's have a look at points, what? Let's take a couple of points. P, 1, 2, 3, and Q, 4, 6, 8. Let's take those 2 points. Now I want to investigate the vector PQ and see what that's got to offer us. Let's put a scale in down here. So 1, 2, 3, 4. In X-land, as high as it goes that we need there. 1, 2, 3, 4, 5, 6. In Y, and 8. Okay, so let's draw that. 1, 2, 3, 4, 5, 6, 7, 8, roughly there. Okay. So let's do some movement now. Point 1, 2, 3. We come out 1, along 2, and up 3. Somewhere like that for our point P. Right? Do you see it? 1 out, 2 along, and 3 up. So we need to have our little box there. Okay. I'm not going to draw the box. It's going to confuse things too much for the minute. So what we'll do is we'll just scrub that all out. 1, 2. Hard to plot this in 3D land. So you don't generally do this. I'm doing this so you can see the idea. This is point P. Now let's plot the point Q. So we come out 4 to here, along 6, and then up 8. So it's way up here somewhere. So that's my point Q. Let's see if we can draw the box between those two. So what's the difference? 1 went out to 4, so we came out 3 in the X, then we came along and 2 in the Y went to 6, so this had a difference of 4 along there. We came out 2, 4, and the 3 went to 8 in Y land, so there was an extra 5 up there. Let's box it and see what happens now. So we draw our box. We've got it out there like that. Just trying to picture these points. Okay, coming along here. Do you get it? Are you seeing it happening here? I hope so. There's a lot of work for Huddy here. Okay, so let's see if we can find the vector PQ now from that diagram. So what we'll do is let's label the points. So this was P and this was Q, and we want that. Let's do it again. Let's work in this triangle down here. Okay, remembering that that's 90, the angle between X and Y, and then we'll work in this triangle here. That's 90, the angle between the Z and the XY plane. Okay, coming down here, what are we going to do? Call this m again. M squared is 2 squared plus 4 squared by Pythagoras. Okay, and then what, this is the one we want the length of PQ, this time not from the origin but between 2 points. And what's that going to be? The length of PQ all squared by Pythagoras is that m squared down here plus this one, 5 squared. Okay, do you get it? Are you seeing it all happening here? So this is 2 squared plus 4 squared plus 5 squared. So the length of that vector PQ should have an arrow on it. Squared is equal to, no, we'll just get rid of the square now, is equal to the square root of 2 squared plus 4 squared plus 5 squared. Because the length of PQ is greater than 0. You should really explain when you're solving a squared equation like that why you've only taken the positive root, because there are really 2 answers to that. Okay, so what have we just done? Well, let's check this out. Let's go up the top here. What is the vector PQ? P going to Q, we found we went an extra 3, displaced point P, 3 in the X and 4 extra in the Y, and 5 extra in the Z. So that was our vector PQ, wasn't it? You can see quite easily how we displaced that point. Let's go down here and do it. P went 2 out here, 4 along here, and then 5 up. So here, we've 3, sorry. So it was, I shouldn't put, what have I got? I've got 1 went to 4, so that should have been a 3 in there. Did you see that? I wonder if you spotted that. So that was a 3 in there, because 1 went to 4, so we come an extra 3. A little mistake there. I hope you noticed that. Okay, so here we go. It's that. So what do you notice here? Well, it's the same formula, isn't it? The length of the vector is the square root of the sum of the squares of the components. We've just added another one on the end compared to the 2D stuff we were doing. Okay, do you get it? We're checking it all out now. We've got our basic displacement idea in 2D land, and now we're seeing if we can extend it. And gee, this is nice, isn't it, to have 2 Pythagoras's here, and therefore just extending it by the extra component. So this is easy. At last, something is easy to remember. It's not a special rule for 3D compared to 2D. Okay. All right, so just check that out, that idea of displacing the point. I'm sorry about that error there, because 1 going to 4 in Xland is an extra 3, and I put 2. Not good. Okay, let's come down and have a look at what we just found. Okay, I've got here my summary of what's happening here. So if we have 2 points in 3D land, so they've got 3 coordinates, what do we do for the change in displacement? Exactly what we did before. The x of the second minus the x of the first. So y of the second minus y of the first. The z of the second minus z of the first. Why? Because a vector can be considered as a displacement of points in the plane. Point A has been displaced to point B. And that's why this still works. And you can see it when you actually try to plot it out and reason it that way. And the length of AB was friendly as well. Right? It's still the square root of each of the components squared. And it shouldn't be take, it should be plus in there. Okay, square root of x2 take x1 squared plus y2 will take y1 squared plus z2 take z1 squared. Okay. So it's just the extra component added on at the end. Isn't that great? Friendly for you. Okay, come on down and let's do some examples from, this time this is from Pearson's again. So we've got 2 points, find the components of vector AB, BA, and then 3 times, so that's a scalar times it, find the components of OA plus OB, and calculate all these values here. Okay, so the most important thing here is if you're finding vector AB, it's OB take OA if you like, or it's just this one minus this one. Okay, but let's have a look. OB take OA. Why have they said that? If you take O to A and O to B, this is explicitly mentioned in the course. So the vector AB is it true? It's vector AB, A to B, would be displaced, and that point there would have to go minus OA. It equals, now let's just get this right here, it equals minus OA plus OB, isn't it? To go that displacement's the same as OA, neg OA plus OB. So that's explicitly mentioned in the syllabus, or you could write it as OB take OA. So you must know that, but I think the quickest way of getting over here the vector expression for AB is this one minus this one minus this one, etc. Okay, and there they are there. But this is naughty, this is very naughty, this answer. It's explicitly mentioned in the course that you must write vectors as column vectors, alright, like that, not like this one. No. Okay. Since BA is the opposite of AB, I don't like opposite, it's going in the opposite direction, so you'll multiply all these by neg 1 for the opposite direction. I suppose if you wanted to, you could get the coordinates of A and subtract B, go back the other way, but you've already done it this way, so multiply it by neg 1 is the easiest. 3 times AB, again that should be a column vector, so you just multiply each of the components and get this answer, 9 neg 27. You must put it in column vector form. OA plus OB, you can work that out because these are the position vectors, so the OA is just the coordinates of the point. Let's go back up and have a look at this. So OA, what would OA be from O to A? It's just the coordinates of this point, isn't it? So it's neg 2, 3, 5 coming from the origin. Remember, the position vector has the same components as the actual coordinates of the point coming from the origin. Okay, and again the square root, the square root of the sum of the squares of the components, so you just get each of them, there it is, and add them up. Okay, and the same for each of them. AB and BA should have the same length. And of course, 3 times AB, all of these then are squared and added. Okay, so that's a good one there. I think you can see it's not too hard now to go into 3D land. All the things are pretty much the same. Okay. Is that all? Let's have a look at what they've got down here. Obviously the length of 3 times AB is 3 times the length of AB, yes. And what, I don't know what they've got here. Oh, here. You can't split it though. If you find the length of the sum of the two vectors, it is not equal to adding up the separate lengths of the vectors. So you might just note that. You can't add up the lengths and say it's equal to the length of the sum. Why is that? Well, OA is there, OB might be here, and OA plus OB would be same as that out to there, so it'd be that, wouldn't it? That'd be the sum of OA plus OB if we went head to tail, or the parallelogram rule either way there, and this vector in here would be the sum, which would be OA plus OB. So its length is not just the sum of these two, is it? They're not all in a straight line. So it's not going to be the sum of the other two lengths unless it was all one straight line. So it's not equal to that. That's what they're saying. Just think about what the addition of vectors means. It means the overall equivalent displacement to these two displacements around here. Alright, let's look at some more examples. What we're doing, remember, is going through what we've established for vectors in 2D in a 3D situation. Okay, determine the relationship between the coordinates of this point so that the points M, A and B are collinear. That is, lie on a straight line. Okay. So for the points to be collinear, it's enough to make AM parallel to AB. That's fair enough. So one is a scalar multiple of the other. You could put K or T. So let's work out AM. We don't know where M is. So if M is just the point X, Y, Z, so they've left that out. Let M be the point X, Y and Z. Then AM is what? Here we are, A to M, X take 0, which is just X, Y take -1, which is Y plus 1, Z take 5. So there's the trick that I haven't mentioned. Let M be a unknown point X, Y, Z. And you're saying it could be any point such that that vector AM is a scalar multiple of the vector AB. So let's work out the vector AB, A to B. So it's 1 take 0, then it's 2 take -1. Uh-oh, made a mistake here. AB, now that shouldn't be there. 2 take -1, that should be 3. 3 take 5, that should be -2. They've put down the vector OB. Oh, haven't noticed that before. Okay, so just notice here, they're working with AM being T times AB. That should be AB. It's not. It's OB, isn't it? Okay, well anyway, we'll leave it at the moment, but let's work out what's happening here. When you multiply T by each of these, that's your vector. So you can say X must be T, Y plus 1 must be 2T, Z take 5 equals 3T. So there are many vectors which would be parallel to AB. So that's this is called parametric equations. That any T that you put in there will give you a particular a point M which will be parallel to AB, will give you a line AM parallel to AB. Just notice that there. Okay, so if we expand upon that a little, let T equals 1, that's one lot of a multiple of AB. M will be the point X is T, Y plus 1 is 2T, so Y would be 1, 2 take 1, Z take 5 would equal 3, so Z would equal 8. Okay, so that's one point from A to M, A to that point which would be parallel to AB. You could let T be anything. T is 2, etc., or T is even a negative number. And when you join up A to it, you will get a vector parallel to AB, because what we want is up here. Watch this now. If you want it to be collinear, it's got to share a point on the line. So there's AB. It's got to share that point on the line and be any multiple. So times by T, so M could be there, and so on, times by 2. So if you multiply that vector length by 2, then M is going to be further out, etc. So that's the idea of a T multiple of that vector length, and that vector direction, of course. Alright, so there's multiple answers there. Okay, try and get your head around that one. We'll practice that in a minute. Let's have a look at the idea of unit vectors. And we said unit vectors on the axes were called I in the X. Should have labelled axes here. I've taken this as a screen clipping. Should be labelled. A J in the Y, and now we put K in the Z. So can you see we're duplicating everything that we did in 2D land. That's all there is to it. Okay, so let's explore that a bit more. And if we come down here, you can see that if we're looking at the vector OP, then what we usually say is it's got components X, Y and Z. And what that means in these unit vectors in the, how I label this again, in the X, the Y and the Z direction, means this is equivalent to X lots of the I vector, Y lots of the J vector, and z lots, let's get this right, z lots of the k vector. Okay, so here they are, the little unit vectors sitting on the axes, and we have to multiply those by the equivalent x component. So we get the length along those axes. So it's x lots in the x unit vector direction, y lots in the y unit vector direction, and z lots in the k unit vector direction, in the z unit vector direction. Okay, so it's just the same thing again. We're just adding on another unit vector in the z direction excuse me, and writing it out in a fuller form. Okay, let's go on. What about unit vectors of any vector? Okay, so let's take a vector. I take 2j plus 3k. And what we've said before is if you want to make a unit vector in the direction of any given vector, what do? Well, you keep the vector and you divide by its length, because that reduces it down to 1 unit in length. Let's have a look at it. So let's take this one. What is its length? Well, the components are 1, neg 2 and 3. So the length is the square root of 1 squared plus 2 squared plus 3 squared, which we've just established up there, root 14, just another Pythagoras on the end. And therefore the unit vector is 1 root 14th of that. So it is 1 on root 14 by I, neg 2 on root 14 by j, 3 on root 14 by k. And you could verify it back here, check it. So what's the length of this final vector? Square root of that component squared, this component squared, this component squared, and it comes to 1. All right, as you would expect. So it's the same stuff in 3D land. Okay, so fairly straightforward there. Let's come down and look at some more examples, and then we'll do some with 3Ds. Find the vector with magnitude 2 that makes an angle of 60 with a positive x-axis. Well, this is peripheral to the course actually, but it could be asked. So what do we say? What's the angle the vector makes with the x-axis? The tan of theta is the what? The y component over the x component, which is the sine of theta over the cos of theta. Okay, so the y component and the x component of our vector should be, what will this be? Sine of, oops, I put it upside down. When we put a vector, we put the x and the y. Okay, so we should have here the sine is the cos of 60 over the sine of 60, because this is y over x in terms of the coordinates. So here we write the vector like this, so therefore our vector is going to be, if you like to write it in the other form, cos 60 by I plus sine 60 by j. So either form would do. So this is either, now you know the cos of 60 is going to be half sine of 60 root 3 on 2. Now, or you could put it here as they have, a half I plus root 3 on 2j. Now we want a vector with magnitude 2. What's the magnitude of this one? Magnitude of this one, if you check it out, these are sides in a right angle triangle, aren't they? So this has a size equal to 1, so that's already a unit vector. So if we multiply the whole thing by 2, then let's call that the vector v as they have would be 2 lots of that vector. Okay, so we can construct vectors at an angle to the x-axis there in 2D or in 3D using the tan of the theta idea. Right, find the direction of magnitude of the vector, this thing here. The magnitude is the easy one, it's the square root of this squared plus this squared. And notice there's no k. If you wanted to put it in 3D land, it's no k. And The direction of it, well, the direction of it now, this is interesting. This is peripheral to the course, this one. So you could do the same thing again. The x component and the y component of the vectors are the cos and the sine. Remember, here this is the y component, which is equivalent to the sine of it, and the x component is equivalent to the sine to the cos of the angle. Okay, so we can put down these statements there. The cos of it is going to be the component divided by the length, and here again the same thing for this one. I wouldn't worry too much about this one. This is not explicitly mentioned in the course. It's just an additional one where you try and find the angles that the vector makes with the axes, and we can leave that as such. You're solving the equation then, and theta is neg pi on 6. So I think probably leave that one. It's, going through it here because it is mentioned in the textbook, but those direction cosines, direction angle with the axes are not actually in the course. Okay, come down to example 6. Find the unit vector that has the same direction as this one. What is the length of this one? Square root of x component squared, y component squared, z component squared, which is 3. The unit vector therefore is a third of that. So if I third all of the components, then I'm doing 1 on length of v by v, and that should be a unit vector in the direction of v. Okay, let u be the vector in question. Here in the second one, length 6 is parallel to that. So we want this one's direction, so it's the same thing again. So the direction of this one, and then multiply or divide by its length. Okay, so I don't like this setting out. I'd rather you looked at producing a unit vector like this. Unit vector is equal to, where are we? I take 2j plus 3k and multiply that by 1 on the length, which is a root of 14. That's squared, and that's squared. Okay, so that's unit vector. So required vector will now be equal to, it's got to be what, 6 units in length, so it's going to be 6 times 1 on root 14. I take 2j plus 3k. Just a little bit of a different setting out, rather than saying let u be the vector in question and v is the unit vector in the direction of v. Yeah, so I'm doing it slightly different. Let's make a unit vector of the given one because we want its direction, because it's parallel to that. Okay, just remember, if we want a vector parallel, it's a multiple of it. You've got to have the same components. And what multiple do we want? Well, we want a unit vector, and then we'll multiply it up to get a 6 unit vector in that direction. Okay, anyway, you like to think about it like that, as long as it's consistent there. Alright, here are some problems from Pearson's, and let's go through and see which ones are appropriate. So this one's good. This is okay. Yeah, not explicitly mentioned in the course, part 3. You could have a go there. You could find the symmetry image C of B with respect to A. Well, that's an interesting one. You can have a go, not explicitly in the course, that one. Given a triangle, yep, this is definitely something you need to have a look at. Determine the fourth vertex, yes. Okay, let D be the point X, Y, Z is the clue there. Okay, and you can pause these as we go. Let's have a look at question 7. Yep, so that's a good one. This is a good one. Right on the course. Some of these others are extending outside the course. This is a good one to have a go at. This one, yep, all of this then. Okay, so have a go at all of those, and let's have a look at the answers then. Okay, 1 and part of 2. Just check your numbers there. The rest of 2, B and C. Don't forget, column vectors is explicitly mentioned in the course. Let's have a look at question 3. Rest of A there. Have a look at B and C. Question 4. And let's look at 5. Okay. Question 6, A and B. And C. Questions 7 and 8. Question 9. Question 10. And question 11 and 12. Well, I hope you're building up some skills here. A lot of practice needed. What I want to do now is answer your question. What is your question? Well, can you find the angle between two vectors? Aren't we up to that? If we're looking at things from 2D into 3D land, let's have a look. Can we find the angle between the vectors? What does the scalar product look like? Well, it's the same thing with an extra product added on. The scalar product, remember, is not just a product, it's the sum of the products of the x's, the y's, and now the z's. Now, I'd like to give you some justification for this, although it's not in the course, to know how to get all this stuff. I do want to give you, other than just a rule where you're following sort of monkey see, monkey do, and you don't understand what's going on. Let's have a look at why that is so, that the scalar product in 3D land is that much plus that extra product on the end of the z components. It's probably what you would expect. Do you remember this diagram from the last presentation where we used the cosine rule to actually establish the scalar product? Now, imagining this diagram in 3D, then V would have 3 components, U would have 3 components, and if you look back at the derivation in 2D, you'll find now, because the distances are the square root of the sum of the squares of the components, it will involve this Z component in both cases, in all 3 cases. It'll now have a Z. But that will be on the end of the length vector, which we've now established as this. Okay. And therefore, it will just be another expression, Z2 take Z1 squared. Because that's just on the end each time, it actually involves, if you look at that derivation again, just the 3 components now. So that the dot product will be whatever we had before, A1 B1 plus A2 B2, and now plus A3 B3, because it's based on the length, and in 3D that's extended by just one more difference of the component squared. Alright, and of course this was the derivation. This is how we came to find this product here, V dot W. It was an interesting sum of products, actually. All of this now was necessary. It came out of this application of the cosine rule to that figure. It was an interesting arrival of that little product there, or the sum of those products. And so we have this form. And we'll look later on, this is actually given on the formula book, in the formula book provided by the IBD there. Okay. Let's have a look at using that in 3D land now. It's exactly the same idea, and here we've got 2 vectors if we want to find the angle between them. The dot product now is 3. terms here. So it's 1 by neg 3. There it is. Neg 2 by 6. There it is. And then 2 by 2 is 4. There it is. So we have that over the square root of the sum of the squares for the two lengths here. Exactly the same, only we have another component, and that's what we're just establishing. Okay, so angle between the vectors is that. Radians, yeah, well you could, but you know, when we're talking about space, in space, we usually put degrees, so just check that. In any exam question they will say to the nearest degree or nearest radian, or to, they'll give you some idea of the units there. Okay, so let's have a look now at this next one. Determine which, if any, of the following vectors are orthogonal. That is not required, that name in the course, at 90 degrees or at right angles to each other. That's what orthogonal means, at right angles. So it's another way of saying, look, check out whether the angle between these vectors is 90 or not. Okay, so let's have a look. Let's check U and V. Are they at 90? Well, let's get their dot product. 7 by neg 3 is that. 3 by 5 is that. 2 by 3 is that. And it comes to naught. Therefore, U is perpendicular to V. You could put it like that. Or at 90 degrees. U dot W, let's check these two. What's their relationship? 7 by 1, same thing again. And that comes to 9. Okay, so if you remember the definition from just above, the cos of theta is the dot product. Okay, dot product divided by the two lengths. So the only way that's going to give you a 90, cos of 90 is naught. So all we have to check out is the top line. We don't actually have to find the bottom. Because if they're at 90, the angle, cos of 90 is naught, so just U dot V has to be naught. The only way a quotient can be 0 is if the numerator is 0. So it's sufficient to check whether U dot V is naught. Notice if you want the actual angle from 9, you'd have to divide by the lengths, and that would be the cos of the angle. So just keep that in mind. V dot W, same thing again, and this time they came to naught, so V and W are also, you can use the sign perpendicular. V is perpendicular to W. Okay, it's the same stuff, isn't it? Just with a extra component added on, because we don't live in a flat world, mate. It's 3D. Okay, so we've got these three vertices of a triangle. Now do not do this. It's very nice for Pearson's to provide this for us, but you're not going to be able to draw that accurately enough. You saw the difficulty I had in actually drawing that by hand. Okay, so we can get good software to do that. So don't actually try to draw this. Do not draw in 3D land. So what you'll have to do is to just do a triangle like this. You say, well, here I've got A, B, C, and I don't know where the 90 is. And I'll just go through all the operations, but don't try to 3Dify it. Just look at this basic shape here. So it's a 3D, so we want to know whether the triangle is right angled and find its area. So what are the three vectors making up any of these triangles? Well, come over here. It's AB and AC and BC, or in any order, it doesn't matter. So let's look at AB. So it's this one minus this one. Then it's this one minus this one. Then it's this one minus this one. Okay, so you get that vector. Okay, or you could put it as neg 4, 0, 1. No one says you have to work in IJK. AC, same thing. Right, difference in components. Okay, x component of C minus x component of A, y component of C, y component of A, etc. Okay, so this would be the vector 0, neg 6, 0 now. Okay, no x component or z component. And same thing here, BC, so this is the vector 4, neg 6, neg 1. Be flexible, write it in either form. The general rule is if they mention a vector in the formulation of the problem, and that's in component form, stay with that column vector. If it's in IJK form, give your answer in IJK. You can switch forms if you wish, but the answer should be stated in the same form as what the problem was given, how the problem was formulated initially. Okay, so we're going to try to find if it's right angled, and if you dot A, B and AC, you might have to try a couple of others, A, B and AC, or you could try A, B and BC. There are 3 angles you could try, aren't there? Yeah. But they know the answer. AB dot AC, so AB dot AC, always working out from A. That came to naught, and so that must be 90 in there. Okay, come over here. You don't have the luxury of seeing it like that. Okay, you won't actually know which one. So they haven't really answered the question as you would here, because you would try a couple of dot products before you realised A was the 90 degree probably. Because you could do, what would you have to check out? If you started with AB dot AC, that would be alright, you'd be right on it. But you might have started with, CA dotted with CB, checking out this angle here. Or you could have started with BC dotted with BA, in which case you're checking out that angle. Notice what I'm doing. You always start at the angle and work out from it for that internal angle. Work outwards, okay, to get that angle between the vectors and not the obtuse version of that. Okay, so you'd have to try all of those. They happen to know that that's a 90 because looking at this over here they've done that, but you won't be able to detect that yourself. So what's the area then? The area of the triangle, you can use half base times height. So it's a half AB times AC, and just those lengths again. Okay. So can you see what we did 2 presentations ago? Right at the beginning I said vectors is an interesting way of handling geometry, and it is, isn't it? It's quite neat. Okay, thinking about coordinate geometry versus the deductive geometry and now vector geometry, we're trying to do exactly all the same sorts of things, and it's quite a neat way of going about it. Let's keep going now and see what you think. Okay, here are, and I'm just coming down to Pearson's questions here. Here are all the things that are given in the formula book now, because we're coming to the end, towards the end now of the vector unit. So here they don't give you a 2D version of the length of the vector. The dot product is geometrically that, or best thought of probably like this, because I delivered this from the point of view of trying to find the angle between 2 lines and thinking about those lines as vectors. So we went searching and we discovered this form really, and then how to get it, how to get u v dot w or u dot v, whatever, is the sum of the pairwise products of x components, y components, z components. This one you might say, what's that? Well, let's have a look over here. Vector equation of a line. That's our last presentation, talking about can you get an equation for a line in Vectorland. We haven't done that. Think about what we're doing here. We're tracking through basic geometric principles on a plane, but with a vector approach, not a coordinate geometry approach. So y equals mx plus c is great for coordinate geometry, but we're in Vectorland and it's going to look different then. Okay, let's go down and have a look at some problems now. Okay, 12.2, question 1 and 2. I think that is fair enough. Have a look, there's some tricky ones here. I might have to think about that, but they are right on the course. Remember, orthogonal is not a word mentioned in the course. They will say at 90 degrees. So let's just interpret that there. Okay, let's go down, have a go, pause it, and let's go down to the others now. I think there's about 20 of these. Show they're both perpendicular. Now that's better. Perpendicular is at 90 degrees. That's a word expected in the course, not orthogonal. Find 2 unit vectors that are perpendicular to that. Plot the 3 in the same coordinate system. Well, as long as that's 2-dimensional, that's okay. Don't try to plot things in 3D. You saw how hard it was when I was doing it. Find the direction cosines of V. This is not in the course. Okay, those angles with the 3 axes are not in the course. Okay, determine that is in the course. Yep, orthogonal is 90 again. Angle between vectors, that's certainly in the course. That's what's mentioned. I think when persons were writing the book, the course was being finalised and they've covered all bases, which is good. Okay, that's certainly in the course. This one, all the angles in the tetrahedron. Well, you could. That's a lot of work, that question. I don't know whether I'd do that, but it's in the course. With all the angles there's a lot of angles that you have to look at between all sides there. So you have a look at that one. Have a look at the answer. Question 11 to 17. Total surface area of the tetrahedron. Well, you could do that. That's a bit long. And in this case, don't forget, the area of a triangular face is half the product of 2 sides sine of the included angle. Remember that, way back. Okay, not just half base times height. You must remember that one as well. DC, make with each of the coordinates. This is not in the course, the coordinate axes. I think all the rest here is okay. Yep, vectors are parallel. Remember, vectors are parallel. A is parallel to B, implies that A is some scalar multiple of B. Okay, the one's got to be K times or T times the other one, and see if you can work out what that vector would be. 17, 18, 19 and 20 are all good ones. Just remembering here, vectors should be written as column ones. That will be the way they're presented in the exam. Column vectors, orthogonal meaning 90. This is not really in the course, this sort of proof thing. You can have a go and have a go at the last one. Bit of a challenging question there. Okay, well, let's have a look at the solutions to that now. Ready for the final presentation on the equation of a line in vector land, or the vector equation of a line on that 3D plane. All right, question 1. Have a look there, check your answers. Question 2 and 3. Let's come down a bit. Question 4. See if we can get C on there. I'll just go up. So there's B, part of C. Go down to C and D. Question 5 and 6, part of 7. There's 8. Part of 9. See if 9's a bit of a big one here. I think 9 is a bit outside the course there. Go to 10. Rest of 10. A lot of work in 10. They give that one a miss, I think. 11 and 12. 13, 14 and 15. Sixteen, 17, 18, 19 and 20. Well, are you scratching your head or are you getting some confidence? Right? You might have to talk to your teacher about some of this as we move on into the final presentation, the vector equation of a line. Anyway, hope to catch you then. Cheers for now.